Uber handles billions of trips and deliveries and tens of billions of financial transactions across earners, spenders, and merchants every quarter. LedgerStore is an immutable storage solution at Uber that provides verifiable data completeness and correctness guarantees to ensure data integrity for its transactions. Kaushik Devarajaiah is the tech lead for LedgerStore at Uber. He joins the show to talk about scaling Uber's data infrastructure. This episode is hosted by Sean Falconer. Check the show notes for more information on Sean's work and where to find him.
Kaushik, welcome to the show.
Thank you, Sean. Good to be here.
I'm really looking forward to this as we were talking pre-recording. I love these stories about scale. You've been at Uber for 8 years. I'm sure you've seen massive scale during that time. I'd love to start there. Can you talk a little bit about your journey at Uber? Like, what was it like when you joined and going through this sort of hyper growth stages to where you guys are today?
It was about 8 years back since I started working at Uber. And at that time, Uber was one of the really nice companies to look out to. And I was very excited to be part of the journey to actually also affect, people in real life. And I worked before in a company called Flipkart back in India. So there I was sort of playing around with data warehousing. So that's where I started. My interest in data actually had started. So when I joined Uber, I started with the data infrastructure. I was lucky enough to be part of one of the early members of the data infrastructure, where we were building out large-scale data ingestion at Uber. So the problems at Uber are slightly different in the sense that this data that's getting mutated, like trips are being taken on the fly, and we have to be able to ingest them for analytics at Uber. Because these are actually used for making real-world decisions that affect the riders and drivers, etc. So that was a pretty challenging problem, a large-scale data ingestion. So we had to build something from scratch. And I closely worked and also contributed a bit to the Apache Hoodie as well. So that was my journey in data infrastructure. And after that, after a couple of years, I moved on to the storage infrastructure, where the challenges were completely different. So in data, it was all about batch systems, throughput, and those were the parameters to actually improvise. But here it was about availability, online storage system with latency and all those guarantees. So very contrasted problems, but that was exciting. As long as it was challenging, in a computer science way, it was pretty exciting to be here.
Mm-hmm. Yeah, absolutely. When you were initially your first role there, working more on sort of the analytics, data warehousing side, what was that tech stack at that time?
At that time, we had multiple architectures. We went through a couple of architectures. Initially, we just had a basic architecture of having HBase as a source of truth for analytics, where we used to use that as a store for actually stitching up rows of the incoming rows that is coming from the OLTP systems, and actually have a job to actually dump data from HBase to the HDFS. And then, so basically a Java, HBase, and mostly these for the stack. And then we had something called Spiper, which is probably built on top of Airflow for the job scheduling, and also a bit of Scala at that time.
Obviously, Uber there's lots of drivers, lots of customers, many rides. It's probably hard for many of us to even fathom the amount of data that Uber's processing. But before we get too far in the weeds, I also want to take a second and kind of just help shape the problem space. What kind of data scale are we talking about across these different systems?
I guess it depends. So, for example, if you're talking about the data infrastructure, in the data infrastructure, this data scale is quite massive. We have hundreds of terabytes of mutable data being ingested and immutable data. So I say they are different because certain data you don't need to they're not like events. Events, they don't get mutated by definition. So their ingestion for them is you don't need to stitch them. That we call it as immutable data. So that the scale of that was in petabytes scale, or tens of petabytes scale, and then at that time, so the immutable data was hundreds of terabytes scale, and I'm sure now it's much more. But yeah, that was the scale at that time, and especially because we had a hockey stick kind of a growth, so we couldn't expect what was exactly the size of data that's going to be, because it was just constantly growing at that time.
Mm-hmm. What were you using for events and streaming in terms of the technologies there?
So events and streaming has always been Kafka. So Kafka has always been the message queue that we've used as a a interface of sorts between the OLTP systems, like a CDC flowing from the OLTP systems to our data infrastructure. So Kafka has always worked pretty well for us with regard to that. That was mostly the streaming system at that time.
In terms of the application stack and application storage, what are some of the unique challenges that you ran into there, and which led to decisions that you had to make in terms of building certain types of technology?
So some of the challenges, right? For example, so schema was something that was probably not enforced as much in the data. So we had to actually fix a lot of the data to be schema compliant. And this is a pretty challenging task in the sense that this data continuously evolving, right? We can't stop the evolving of the data. We have to reach out to the creators of the data, the other teams, and also have a conversation regarding to have the data to be schematized and also keep the ingestion flowing without any hiccups. So there were some interesting problems that you have to solve. It's not always a perfect with respect to data, but you still have to solve the problem for the company to have the business flowing. So we had to do something like infer the schema and then use the most basic version of the schema, like use strings, because strings is the most generic form. It can work with even for ints and floats in a way, and then have that sort of interpreted better when you read the data. So these were some of the challenges that we had to know, and that was one. And apart from that, scale is definitely one of the challenges because of the sheer large amount of data and that we had. Like all of the systems had to be like scaled. For example, HBase, or for that matter, we use Spark. I forgot to mention Spark as one of the technologies that we used in the data infrastructure. And even these jobs, the Spark jobs which ran, had to be scaled accordingly. And there's a lot of levers that come into picture, whether it comes to memory or like a disk usage, etc., that need to be optimized to have your jobs working seamlessly in the face of continuous growth of increase in data.
In terms of the schema, like consistency was part of the challenge there is, people are maybe creating like new table structures or new structures of the data, depending on like what problem they're trying to solve. And then those decisions are being made at like a team level and not coordinated across the entire organization, or like certain foreign key constraints if you're using structured data aren't enforced. So basically the data gets dirty over time.
Exactly. So in a way, and then we started developing like formal sort of end-to-end processes to actually have this, I would say, like an interface between end-to-end sort of lights from the moment the data lands, like a database lands into analytics. You need a way to have the conversation between the two systems, right? So you need sort of like an interface definition. So we formalize these through like Avro schemas and various kind of schemas within Uber, which became first-class citizen. And that was a very fantastic part of the maturity of the systems that we had grow at that time. Today, I think schema is like a first-class citizen. Although we use NoSQL databases, schema is always a first-class citizen.
What is LedgerStore and what does Uber use that for?
LedgerStore is a sort of like a specialized database of sorts we can call at Uber. And it's been designed to actually store ledgers. And ledgers, for example, is basically can be thought of as an immutable sort of set of data. And we say immutable, for example, events in life that happen, for example, are sort of immutable, right? Because they are indisputable. And what is the reason that we want to perhaps store data in such a fashion? One main reason that we can think of is the audit trail. There are a certain set of use cases, for example, financial use cases, where this is sort of a standard practice across the industry. Any sort of events that, for example, affect the balances of, let's say, a wallet, the additions or the subtractions, the credits or the debits, etc. These are sort of need to be maintained as a trail. And the reason being that there's a way to actually, by maintaining a trail, we have a way of actually going back and verifying what happened to the history of these balances. If you don't maintain a trail, what happens is if you just keep updating without having a trail, it's hard to identify any issues in the system. So that's why ledger databases are used, which is it's basically a log. It can be thought about as like a log, where it's easy to go back and verify, hey, this is what happened to this sequence of events. At Uber, coming back at Uber, some more context, right? So we have like millions of riders, drivers, and other parties that are using Uber. And there's a lot of transactions that are happening. So there's like billions of dollars of transactions happening every quarter. So due to this sheer scale, it's very important to be able to provide data guarantees on data correctness and completeness. So that is where LedgerStore was born.
In terms of ledger database, is it the case that like all entries in the ledger, they're always going to have some sort of like time event essentially associated with it? So you can think like payment transactions logs is another one that you mentioned. So they're always going to be essentially of like a moment in time, and that's why they can be an immutable object.
Absolutely, yeah. So ledgers, they generally have a time associated with them. There's a specific definition we call for that. And that's also first-class citizen for ledgers, because it doesn't make sense to write a ledger ahead in future, because time is not in future. And that is an important aspect of a system property.
Mm-hmm. Why use DocStore as the data storage medium for LedgerStore? And what was involved essentially with some of the migrations that you did through each of these evolutions of LedgerStore?
Yeah, sure. So DocStore is one of the kind of matured systems at Uber, databases at Uber, serving a lot of various kinds of workloads for various like tier one use cases that we have. So historically, Uber has always had like a storage experience right from the beginning, so where we basically built something to actually scale at that point of time. So DocStore specifically was something became generally available around 2020 or so, if I'm right, or 2019, 2020. So by that time, LedgerStore was already live. So we had to make a choice of the database at that time. That's the reason we went with DynamoDB. And so when DocStore went generally available a couple of years later, considering the fact that it is a distributed database and it provides the availability guarantees, high availability guarantees that we need, good latency guarantees that we need, and it provides shard local transactions, rich query support, and all the requirements that we sort of wanted. And it was a good choice for us to actually choose and to actually also have a team within Uber, which is supporting DocStore. So it was a good choice for us to actually, alternative for us to consider, and to also sort of consolidate the kind of databases that we use internally. So that was primarily the reason.
So DocStore is like Uber's homegrown distributed database system that uses like a doc storage medium like other sort of NoSQL types of databases. Is that right?
Exactly. Yes, that is correct.
In terms of like building one of these distributed database systems, like I feel like this is a journey that a lot of companies at massive scale kind of reach at some point. And I'm curious, like, is it the case where at some point when you reach just, such scale that you really just have to essentially like roll up your sleeves and build something because the scale problems are so specific to like your company, your use case that maybe something, off the shelf or built somewhere else isn't going to be specialized enough to essentially address the types of scale problems that you're running into?
Absolutely. And if I remember correctly, there's a deck somewhere that I've gone through where it actually shows the kinds of challenges that we had earlier in Uber. The scale was just like a hockey stick example, right? The scale was just so high, so you had to think exponentially, couldn't think incrementally anymore. And so that is actually the reason why the previous system, which is like a distributed sort of database system, was actually developed at that time. But we started thinking like in a distributed fashion back then itself. DocStore is basically like a sharded MySQL. It uses Raft for consensus. So we had a sort of a similar system ahead. And DocStore has some more features than the previous system. But regardless, to answer your question, so we started thinking, Uber as a company started thinking about it long back to be able to scale to these needs continuously. Because it's just a single instance would just not suffice. There's only so much you can do with vertical scaling. So to be able to give sufficient confidence to the business, we had to do horizontal scaling at that time. Like you said, yes, taking advantage of the specific nature of the business, we had to build something. DocStore had to be built internally.
I mean, I think you raise an interesting point there where if you're growing exponentially, your data is growing exponentially, then doing something that maybe sounds on paper under normal circumstances, like efficiency gain, you're getting like, oh, we like improved by 20% or 30%, like isn't really going to buy you that much runway if your data is scaling exponentially. You need exponential solutions essentially to address exponential growth problems.
Absolutely.
In terms of like some of the effort to go around that you had to go through in order to migrate these different data stores, like how did you manage to migrate 250 billion records without any downtime or data inconsistency?
So migrations are generally quite a bit of a challenging thing, especially considering the requirements. So depending on the requirements. So for us, specifically, since LedgerStore is like one of the top tier sort of services, which is the source of truth for the Uber's money data, we can't afford to take a downtime. And so availability has to be high, and the performance also has to be high in terms of latencies and throughput. The reason being, there are other systems that are dependent on these systems. So there can be a cascading effect if we regress. And consistency. So another thing about LedgerStore is it's strongly consistent. That means you write something and you read back, you're guaranteed to see the data. And that's a guarantee that is a first-class citizen that's provided by the system. And this is something that we need to uphold even during a migration. So these three sort of properties were the sort of the definition that we started with as sort of the requirements for the migration. And we added some more properties such as reflex sort of reversibility. Like in case during the migration something bad happens, you need to be able to go back to the previous system, and you can't afford to say, "Hey, sorry, this system has some kind of issues." So again, downtime is not allowed. So these are some of the properties that we went with. So to perform this, the migration was sort of carefully designed. So one thing about LedgerStore, right? So it, like I said, it provides data completeness and correctness guarantees, which means data cannot be mutated or deleted, or mutated or deleted essentially. So this is a guarantee we wanted to uphold even during the migration itself. Now, if you think about the migration, there are basically two databases like A and B that we want to migrate to from A to B. And during this time, essentially, it would be nice to have something like a transaction, right? So where you either write to both or you don't write to both. So that's like a distributed transaction. So, but distributed transactions are they have their own challenges to do. That's something we didn't want to do. We want to do something simpler. So we basically it got like three parts. I'll give a quick overview and we can dive in if needed. So the three parts are basically like the historical data, capturing backfilling the historical data, and then orchestrating the online reads and writes between the two databases and ensuring they're in sync. And third part is data completeness verification. So these were the sort of high-level parts that were involved to actually migrate them successfully.
Yeah, I would love to get into the details on some of this stuff. In terms of, protecting the ability to do rollbacks, since if you're writing to both databases and you want to make it transactional where the write happens to both databases or it doesn't happen, is part of that essentially, if you can guarantee that, then it also makes rollbacks easier because you now know that both databases should be the same. Is that sort of the thought process there?
Yes, but we didn't go ahead with that kind of solution because the sheer complexity of that solution. Distributed transaction generally needs the ability for you to be able to roll back something that's partially written. And that's a guarantee we didn't want to lose. Like, for example, in LedgerStore, once you write something, or once you write a set of a record, it's considered as permanent, right? So just because we're doing a migration, we didn't want to sacrifice that property. So we didn't go ahead with the distributed transaction. We went with another approach. And I can talk about that more if you're interested.
Well, in terms of the backfill, so you basically need your B database to catch up to the A database at some sort of epoch before you start writing to both. So how did that work in terms of the backfill? Like, how do you catch up to something that presumably is probably growing at a pretty high rate?
Yeah, that's a good question. So generally, that's like a never-ending game, right? So what we do is we start the online writes on B. Let's say we're moving from A to B. You start the online writes on both of them, A and B, and start doing the backfill. So the backfill, once it's done up to the point when you started the B, you're good enough, you're guaranteed. I mean, in theory, that you have all the data. So it's essential to actually start the online writes and reads, online writes in particular, not necessarily the reads, on the secondary database.
Okay. And then in terms of the other, you basically mentioned three things: is backfilling, then there's orchestration, and then there's essentially like guaranteeing the completeness. So what was involved in terms of orchestrating the writes across both databases?
Yeah, sure. So this is what we call it as dual reads and writes. So one thing that I said was another property that we didn't want to lose was basically the latency. So one strategy we think about is if you're adding the latencies of the two databases, it becomes additive to the end customer. So we didn't want to expose them to this sort of an additive latency. So what we did is we brought the concept of primary and secondary. And the secondary writes were basically asynchronous. And asynchronous also means that it's not necessarily guaranteed to pass. So now you need a way to sort of fill in the holes. When secondary is missing the data, you need to fill in the holes. So for that, we basically built a system called as spot repair, to which actually go and identify the holes and just the holes and then just go repair them. So while it seems straightforward, there's a lot of things to think about in the sense that what happens if the secondary becomes primary and other interesting sort of corner cases that we faced during this. But essentially, important thing that we did was actually treat the two databases as nothing special. They're both databases and not giving special preference. And that's a key, which makes it easier when if somebody is getting promoted to the primary. Mm-hmm. But essentially at a high level, yeah, that was the thing.
And then during this migration, like, did you actually end up having to roll back anything, or was everything, smooth sailing?
Thankfully, we didn't have to, but we were prepared. If at all we had to roll back, we were prepared. And like I said, not treating them special, treating them both as databases, just as primary and secondary, with the roles being interchangeable, that made it possible. So I think having those definitions and modeling them in that way made it very simple. But we were prepared if at all we had to roll it back. We just had to swap the order and then just keep doing the same things that we did with the migration.
Got it. And then can you talk a little bit about the types of indices that LedgerStore supports and what they're used for?
Sure. LedgerStore supports three kinds of indexes. So one is a strongly consistent index. The other is eventually consistent index. And the last one is time range index. And the strongly consistent index is used for the use cases where it's essential that so indexes by definition are a sort of metadata, right? You can think about them as metadata. They're not data itself. When you write data, the indexes appear to point at the data. So this property of strongly consistent indexes, when you write the data, the index is going to be appearing instantaneously. There's not going to be any lag between the two. And eventually consistent index, there will be a lag. It's all guaranteed to be a lag because they are not built in the same online path. They're built in a background way. And the time range indexes are basically used for doing time range queries. We spoke about earlier that, ledgers have time as a first class citizen. And so time range queries are essential to be able to perform various ledger actions like sealing the data, which we do on a time range, or offloading the data.
And then how does the commit work for, say, the strongly consistent indices?
Yeah. So the strongly consistent indices are built with the two-phase commit protocol. So here what happens is that we have two phases. So first, an index intent is written, and sequentially a record is written, and then the index is committed asynchronously. I say a sequence. It's important to do this sequentially and not parallelly, because that is what ensures the guarantee that the two are going to be present, or the index is going to be present if the record is going to be present. The reason being that, let's say the third step, the commit fails. So first of all, when I say an index intent is still means it's an intent. It's not really an index. For it to become a true index, the intent has to be false. It's just like a flag. So the third step, we commit the index. But let's say if the committing fails, upon read time, we have an ability to go and resolve this. We look up if the record is present. And if it's present, we commit it. If not, we roll it back.
Okay, so this is like a two-phase commit, essentially.
Exactly.
Mm-hmm. How do you determine, as a user of LedgerStore, which index to use given a use case? Let's say, I don't know, credit card authorization flow versus a payment history page. How are you making those kinds of decisions about which index to use?
That's a great question, actually. And like you alluded, credit card flows is actually one of the flows that we use strongly consistent index. And in fact, we recommend not using much of strongly consistent indexes unless really needed. The reason being, this is orchestrated in the online path, unlike the eventually consistent indexes, which are constructed by tailing CDC to change it a capture of the database, and then that's how it's built. So nothing happens in the online path for building the eventual. So how we decide which has to be strong, if it's intolerable for the application to actually tolerate this lag of the index appearing, then I think it's strongly consistent index is the way to go. So one of the examples that we actually have is in the credit card flow, where the credit card authorization is done, and later when we want to charge the card, we actually look up this index. And if this index is not found, the flow assumes that, the auth itself is not created. So let me go and do a fresh charge. So it can lead to a double charge for the customer. Even if it happens 0.001%, it's a really bad experience for the customer that we just cannot. It's not a matter of just the amount. It's just a matter of the fact it happens is not tolerable. And that's why we choose a strongly consistent index.
What is the typical lag time for that anyway?
The lag is zero.
Mm-hmm.
Zero. It's absolutely zero. If the record is present, index is present.
What happens if you need to add or drop an index?
So we have basically, as part of this indexing story in LedgerStore, and to step back a bit more, right? So indexes are pretty important in LedgerStore because they look up the source of truth ledgers. So that's why it's important to have a robust indexing story. So when we have to add a new index, so we basically have an automated flows where indexes are going to be built by looking at historical data, and indexes are going to get written historically, and then we have jobs to monitor the progress. It's all automatic without requiring any human intervention. And once it catches up, we have the option of enabling the index or just waiting for the user to actually enable it. So that is for adding an index. And for dropping an index, again, dropping an index, we have to be a bit more careful if it's being used in the online path. So we ensure that there's a new version of the index that's running. So indexes are version every time let's say they're modified. But if it's not versioned and somebody wants to drop it, then it probably would have to be a manual process because we just want to ensure that there's no traffic to it guaranteedly.
Right. Yeah. You want to drop the index and suddenly things grind to a halt, essentially.
Exactly. So just because there's no traffic now, it doesn't mean there's no traffic forever as well. So yeah, we just have to be double careful for that.
Mm-hmm. And then, how long do you keep ledger data in hot storage?
So that is flexible. It totally depends on the business requirements. So there's a need for flexibility because it depends on what is the recency of the data that's accessed most. That's mostly the concept. And in hot, the latencies are very good. And in the cold storage, latencies are higher. So we sort of try to do a balance, such that the P90 or P95 latencies are within a certain sort of range. So we sort of optimize based on that. But the point is that we have flexibility to control the same.
What's the advantage of moving some of it to cold storage? Is it merely like a cost savings?
Oh, yes. So ledgers, by definition, they are immutable. So they will keep getting appended on and on and on. Unlike, let's say, like an RDBMS or let's say any data that gets mutated, right? So the continuous append will increases the storage footprint forever. So that's why there's a need for curtailing this cost of the storage. And that's why we do cold storage offloading for the historical data. If not, like you said, the cost is going to be very high. And also the maintenance is just going to be unnecessarily harder on the hot storage.
Yeah. Are you using anything, existing technology or maybe develop something yourself for orchestration around the creation of indices and other parts of LedgerStore in order to, be able to have certain guarantees on asynchronous jobs completing or making sure that things are happening in the order that you need them to take place?
Yes, absolutely. So we have a jobs mechanism to actually create jobs and then orchestrate them. So it all happens within the LedgerStore ecosystem itself. And the nice thing is, this is one place where we can control everything. Even if we have to launch, let's say, a Spark job, the source of truth, the brain is like sort of the central nervous system. It's all in one place, which is a nice thing for the design of the system as well. Yes, it's all within the LedgerStore ecosystem.
And that's something that you developed in-house?
Yes, it's all within Uber developed systems.
And then what about in terms of the future of LedgerStore? Like, how do you see this platform, evolving from here?
That's a good question. So LedgerStore in the future, we want to probably add like a materialized view for the ledgers. Like I said, ledgers keep growing in size. They're basically like an event history of sorts, right? We are trying to explore if we could add like a materialized view, like an aggregate snapshotted view. Let's say, let's hypothetical example, right? Let's say I have balance history that is stored in my LedgerStore over time. Let's say $5, $6, $2, $3, etc. And let's say we want to give a snapshotted view, which is like the latest view of consolidating the latest view to actually have as a snapshot view. That's something that we are considering. And we are also thinking about if we can improve the consistency. We are strongly consistent within the region. We're trying to see if we can provide even more stronger guarantees. These are some of the things that we're thinking of.
How much are you paying attention to like what's going on in other distributed databases? Like there's been a lot of investment and innovation in the space in the last 5 to 10 years from a lot of these like hyperscale companies. And some of these things are now available as services or open source projects. Is that something that you or other people at Uber are like paying attention to and seeing how can we take inspiration from here and evolve our own systems?
Yeah, absolutely. When we sort of developed LedgerStore, when we built LedgerStore at Uber, which I think it was like late 2018 or so, there was not an equivalent system. And so that's the reason we sort of went ahead and built something. And it was definitely much effective to build it inside. And that was the reason. And there's always, we always do check, sort of calibrate and see if there's a better possibility to actually import other solutions. Nothing has turned out so far. Especially, like I say, the effectiveness that we have internally by building it ourselves, it still holds. So, but yeah, that is definitely something, an exercise that needs to be done for any company regardless.
Mm-hmm. During this whole like process of working on LedgerStore, like what do you think was one of the hardest problems that you came across from an engineering perspective?
Oh yeah, that's a great question. So a bunch of it. It's fortunate to be able to work in LedgerStore to have such problems. So one of the thing is the sealing component. So sealing is one of the components in LedgerStore which ensures that the data is complete and correct. So essentially what we do is, so we have a cryptographically verifiable way to say that your data is, what you wrote, and it hasn't been deleted or updated by anybody. So it's sort of like a blockchain, but blockchain is like a distributed ledger. It's different in that way, but LedgerStore is a centralized ledger. So we have the ability to seal data in time range buckets, and then sealing also provides a SHA-256 hash associated with the data. But to do this, we want to be able to also have confidence that we have captured this data in the system. So we've built a mechanism to actually obtain the guarantee that this data is definitely committed to the database, whatever the underlying database is, right? It's possible, for example, let's say that I write the data to underlying database, but the database does not have the durability and it loses it even before I seal it. Or let's say it was accidentally sort of wiped out or something like that, right? So we have a way of detecting it. And this is a challenging engineering problem to solve, regardless of what of the database is. So we basically compare sort of the change streams and actually what we wrote and provide this guarantee. And not just that, we want to be able to do it in a more optimal way. Just providing this guarantee is fine, but if you want to do it in a regular cadence, that makes it technically challenging. So that was definitely one of the challenging sort of projects that I did in LedgerStore, apart from, of course, migration itself.
Yeah. So how does that work? Like, how does this sort of like, I don't know, like checksum process validate that this has all been complete?
Oh, yeah. So we basically tail the change stream. We do an exactly once processing on the CDC that's backed by the database. So this exactly once processing is essential to actually count exactly the items that are there in the window. You don't want to overcount or undercount. You just want to count exactly the right number of items. So this exactly once processing is what is done on one side. And the other side, we wrote something. So we have the time range index to be able to give the other view. And if these two view matches, then you have a confidence that this is what it is. This is what is captured into the system. And yeah, that's the main reason of we providing this guarantee.
As we start to wrap up, is there anything else you'd like to share?
Yeah, I just want to say that at Uber, so we are working on various problems to actually sort of make the magic happen. And in this case, the magic happens to be the fact that the guarantee of the data correctness and completeness, and the fact that this is the source of the data that's been actually looked upon even by various end use cases. Because I think this is a pattern that's also becoming in the industry, that the quality of the data is becoming very important. So a single copy of the data is generally a trend that is emerging. And LedgerStore is one way providing that service at Uber by also exposing indexes on the source of truth ledgers. So it can be looked upon by various other upstream and downstream services to actually find out the source of truth. And yeah, I guess that's all.
What do you mean by that? So essentially the LedgerStore is acting as a single source of truth. And then are the downstream services essentially creating just almost like a pointer back to the LedgerStore in order to connect the source while not actually creating a replication of the data?
So what I meant is, let's say, for example, we want to investigate what happened to the balances of a certain user, and we want to go and sort of investigate it. And it can come back to LedgerStore to see what is the source of truth that happened to affect this balance. That's what I meant. As the other applications that use LedgerStore, let me put it that way, they have an easier way to come back and access the source of truth. It's not like the source of truth was written and then you never see it unless there's you want to actually detail audit, but you can actually go back and for investigations as well. You can just go back to the source of truth, and regardless of the size of the data, you can actually go and see what happened and have the confidence that this is right. That's mostly what I said. I mean, they could maintain their own copy of the data, but again, now you have two places to build confidence, right? That's not nice, as opposed to just having one place and trust it.
Okay, makes sense. Kaushik, awesome. This was great. Thanks so much for being here. I really enjoyed it.
Likewise, Sean, and thanks for the interview. It was great chatting with you as well.
All right, cheers.
Cheers.